So the talk of today is about blockchain consensus of economic incentives. And most part of the work actually that I will present today is a work that I've done with some collaborators, particular Yekalia Musugenu, Bruno Bier, and Maria Butukar. So before entering all the details of the talk, I just wanted to make a point about the history of Bitcoin, because when we talk about blockchain consensus, of course, we are talking about Bitcoin somehow. This is the first technology that actually came up with the concept of blockchain, right? And in fact, what is interesting is that from the early 80s, this vision of digital money has been around somehow, but it took more than a quarter century before a fully decentralized solution became a reality. So first tries were systems in which, for instance, we have the concept of untraceability of exchanges. Second tries of systems were kind of discovering how proof of work could also serve as a mechanism to mint money, to create fresh money. And then later in 2000 years, there were this idea of trying to decentralize the way in which actually transactions are validated in the system, in particular to avoid multiple spending and token forgery. Because in the first system, in some sense, there were some trusted entities that were there to avoid multiple spending and token forgery. So the idea was to see if, for instance, visiting quorums could help with that, but this was vulnerable to similar attacks and so on and so on. So there are so many ideas, and then all ideas have been combined in Bitcoin to actually decentralize this validation of a transaction. And in fact, what does it mean is that when you want to decentralize this validation, somehow you are trying to ensure a consensus among participants about the history of the log of the register in which you register transaction, right? And the fact that is you want to ensure that this immutable history can be served as a truth, as a base of truth. This is important because there is no external authority that can do this work, right? So it is not exactly the sense of consensus as in distributed computing, is less formal somehow, and I will go back to this sense after. But the idea is to have this consensus on the status of the ledger. And when you say the status of the ledger, of course, this shared history that we have in the register in the ledger can be anything. Can be transaction for Bitcoin, can be sequence of metal costs for smart contract in Ethereum, for instance, or logs of any data in kind of different kind of applications, industrial applications that we can see around now. So the question now is how to achieve consensus blockchains. And the answer is easy: design a good blockchain consensus protocol. But as what we have seen before, it took more than 30 years to get Bitcoin, right? So it's not so easy to do it. So just to have all the audience on the same page, I will recall briefly how Bitcoin works, the essentials of the protocol. This is very simple. So it's a protocol based on mining. Mining is the procedure to create and append a new block in the blockchain. So block is a set of transaction that is chained to the previous block. And mining consists in solving a puzzle and also to prove that actually the solution has been found to the others. And this puzzle difficulty is that just somehow to have a block every 10 minutes, but by product, the protocol actually could achieve multiple chains at the same time. So somehow these multiple chains can actually appear even though there is no attack, just because a bad behavior of the networks appears and that we have recent different partitions. So the idea is that this is actually taken into account by a reconciliation rule that is a consensus there to choose a unique state of the ledger, which is the unique chain. So you need to choose among these multiple chain, one chain. And this is a rule that you have to think about. And this is the rule that is used in Bitcoin. So in practice, when we talk about Nakamoto cell consensus, we are referring to two different things. First, the proof of work which limits the number of concurrent proposals. When I say proposal, it's not just one block, it could be a chain of block. And the longest chain rule that actually is the reconciliation rule that help us to choose a unique chain in case multiple chains appear in the system. What is interesting is that, which is completely new, and this is actually the point I want to make today, is that Bitcoin brings also economic incentives. This is pretty natural because Bitcoin is about exchange money, which is digital money. So why don't actually remunerate those that works for the system to be consistent, to be stable, to give to them some money. And in practice, this is important because proof of work is costly as a computational cost. So the idea is also to encourage people to choose the longest chain rule and to propose a reward for all the proposals that actually get a consensus. So all the proposals, the blocks that actually fall magically in the unique chain that is chosen by all the participants. Rewards come from transaction fees and also minting fresh coins, of course. What is interesting, when you talk about incentives, immediately you are talking about rational participants. So those that respond to incentives, right? I could choose to invest some hardware and everything in Bitcoin because maybe I want to gain some money from it, right? And in fact, this is so important that economists are also looking at rational behavior inside Bitcoin and to figure out how this rational behavior actually is. And there is a theorem, and it's a nice work from Bruno Biet and other authors that is called the Bitfork for theorem. They say that if agents are profit seekers, then the protocol, so the Nakamoto style consensus that we've seen before, is a Nash equilibrium. This is a really important concept, Nash equilibrium, because it is a way of saying that somehow this protocol is a good protocol. Why? Because if all the others will follow the protocol, I have no interest in deviating from the protocol. And the intuition of the proof, I'll just give you the intuition. Of course, I will not introduce any mathematical notation here in the talk, but the intuition is that, first of all, a miner has a finite resources. Cost is proportional to the number of extended branches, and the miner will get a reward if the branch his block belongs to persists, is chosen by all the others. So if the miner anticipates that all the other miners will extend the longest chain rule, so the good behavior for him, the best response for him is also to choose the longest chain rule. And this is exactly Nash equilibrium. Two observations here are the following. First is from a rational point of view, agent point of view, any common rule is actually a Nash equilibrium. If we have any other common rule, could be you have to choose, I don't know, the green chain out of all the colors that you see. Of course, this is not the case, but just to say that if there is another rule that is proposed by the protocol, this also is a Nash equilibrium. And the second observation is that the protocol is not only the unique equilibrium of the system. There are other equilibria that exist, and these other equilibria are not leading to consensus. This is important because sometimes when you want to design a protocol, we want to check if this protocol is a Nash equilibrium, but we also need to check if there are other Nash equilibrium that exist that are deviating from the expected outcome, which is consensus. So all the works on Bitcoin are so many works. We were interested in another class of blockchains, which is not Bitcoin. I will introduce in a short time. We wanted to study something else because, of course, Bitcoin has some issues. And the first issue is the huge energy consumption, of course. And there are different kinds of estimation, ranging from the most optimistic to the least optimistic. I would say that the cost for consumption per transaction is between 1 and 20 days of an American average household, according to this estimation, which is huge, right? And there's another problem is that, of course, transaction finalization is very slow. It's quite long because you need to wait at least 6 blocks to be produced to consider a transaction finalized in a block that actually is followed from by other 6. And there is also this byproduct problem, is that the fact that if you have multiple chains at some point of time, you could have some conflicted states or multiple states of the ledger at the same time, and you want to then to choose after reconciliation one state. It means that maybe some of the transaction that you had before can be revoked later, right? And this is also can be an issue. So to actually address at least the first 2 problems, proof of stake blockchains have been developed. And the proof of stake blockchain actually are based on a different system. They are not based on proof of work. So to choose actually the leader, that this is very simple. You have in the blockchain the transactions that are registered. So you have the balance of all the participants in the system. You rank the balance, you pick the richest, and this richest is the one that is in charge of create the next block. And each time, of course, you will have balance that will change from one block to another because you include more transaction over and over, and then you will have different leaders for each block. That's an interesting idea, but still there is the problem of a transaction that can be later revoked because this kind of system are not really are really like Nakamoto style consensus somehow. So to actually address this last point and to not to avoid transaction to be later revoked, there is another class of blockchains that emerged. And for instance, this is Algorand, this is Tendermint using Cosmos, this Tendermint using Tezos, in which actually the proof of stake is coupled with a Byzantine fault-tolerant distributed consensus. So it's pretty similar somehow in the principle, because the basic idea is to select not a leader but a committee. But it's the same. This is selected on the basis of the stake, so the ranking on the balance that are in the register in the blockchains, in the blockchain. And then as soon as a committee is formed, this runs a form of Byzantine tolerant consensus. I say form because, of course, purists can say that what is run in Algorand is not the same that is run in Tendermint. There are different algorithms, but the idea is that these algorithms are there to solve consensus in presence of Byzantine adversaries, which means process that can deviate from the prescribed protocol in any possible way. What is interesting here is that the selection procedure for the committee is verifiable, of course. So every non-committee member, so those that are outside the committee, can just verify signatures of the committee, and they don't even need to go for verifying the content of the block if they trust the committee, of course. A transaction here is finalized as soon as it's included in a committee, in a committed valid block. So as soon as a committee produces a block, this is committed and transaction inside are finalized, and this transaction are not revoked later. And I will put here an example. I say that all these different platforms are using different kind of Byzantine tolerant consensus. There is this Tendermint core platform that use a particular algorithm. And what is important to say is that actually this algorithm is as a kind of voting procedure inside. And normally assigns this, if the committee assigns n, we have that n is equal to 3f plus 1, where f are the number of Byzantine participants. So this is the tolerate thresholds. Okay, we cannot tolerate more than 1/3 of Byzantine participants. And the voting procedure to tolerate these guys, it's a bit difficult to explain, but just to give you an idea, in practice, you have always a leader that proposes a block, and the proposal is accurate if actually we have at least 2f plus 1 proposal for the same block that are collected. then any committee member would vote for it. And the committee member finally commits the block when he sees that 2f+1 already voted for it. This is just to be resistant to this Byzantine, but also to be resistant to network bad behaviors. And in fact, that is important to say that this particular class of protocols are resistant to a period in which the network misbehaves somehow. So a block is eventually committed here in an eventual synchronous system, means that after a period in which the block, the network misbehaves, we will have a period in which the network will be well behave somehow. And in any case, even though the network will misbehave for the whole time, no more than one block is ever committed. So we prove the correctness of this particular algorithm, so this standard mint core blockchain, but only in a context in which we have correct and Byzantine participants. So there is no rationality here. We really need to go further. Why I say that? Because of course these blockchains are used as blockchain consensus. So they are also providing incentives to participants, and or at least are supposed to provide economic incentives. In particular, what is costly here is block verification, because in any case you need to verify blocks, but you also to participate as a committee member to the consensus. And there you have communication costs, because voting procedures actually imply communication between participants. And then the idea is to have rewards for all these guys. And this is exactly what happens today in Algorand, in Cosmos, in which we have these kind of rewards. So the question now is exactly the same way in which Bitcoin has been analyzed from a rational point of view. Question is how we can analyze this kind of protocols that are supposed to be also tolerant to adversaries. So in the sense that we want to know if incentives drive this voting-based consensus somehow under a model that is rational. But we also need to include adversarial behavior, right? Because we always have those that want to disrupt consensus. As this is why you have a Byzantine for tolerant consensus protocol there, to be resistant to Byzantine guys. So, and the other question is, when you have rational guys, are you sure that they will coordinate, they will go through the voting procedure as expected? So the basic question is consensus achieved, or also which equilibrium we can have without consensus? This is also something that we want to know. So the exploration started considering that, of course, distributed computing, game theory, that are the two frameworks in which we can put our study, have similarities, but also many differences. In particular, distributed computing is really concerned with the interaction among correct processes with 40, in that case, Byzantine processes, who can take any arbitrary action to disrupt our blockchain consensus. And in particular, as I said before, a Byzantine tolerant distributed protocol is a set of computation and message exchange. In general, you have a program that is executed by each process to solve a given problem that in this case is consensus, despite the presence of Byzantine process. This is the focus in this case of distributed computing. Game theory, it's a little bit different because it's of course about interaction among a set of guys, a set of rational players that are respond to incentives and are respond also to costs, and in which interacting choices produce outcomes with respect to their preference, sometimes utilities, and these outcomes sometimes are not really intended by agents. Okay, so there is some outcome appearing. These are interacting, following their best, the best response, and then the outcome will be something that we need to study. When we say outcome, we are talking about, of course, consensus. And it's important to say that consensus is not something, it's something really formal somehow that actually is stated through 3 different properties. And one is termination, which means that in the case of our committee, it means that eventually a block should be produced. So every non-adversary participant commit on a value. Agreement, if there is a non-adversary participant that actually commit on a value, in a block, the other that is not adversary should also commit on the same value. And then we have validity, which say that the committed value should be valid. And when we say valid, this is completely application dependent. This is also called external validity. By the way, Christian introduced this concept some years ago. And in our case, validity here is the validity of the block, so validity of transactions, validity of signatures, and other stuff. By the way, in the rest of the talk, processes, players, and participants, I will actually use the terms in a way that is interchangeable. So to study our problem, say consensus with rational players, with adversaries, and with protocol, that actually is the way in which these agents interact, we need to find a unified framework, right? To do it, we assume then that all players are rational, okay? And all of them play best responses, but they can have different preferences. On another terms, we have 2 types of players that are opportunistic, in which they just maximize expected net rewards, and adversaries that seek to disrupt consensus properties. So the 3 properties that we have seen before. And under this framework, we can formalize the voting procedure as a dynamic game with asymmetric information. Why? Because players, in particular opportunistic players, doesn't know who the adversary are. And and make an analysis to see if consensus arise in this game under a solution concept that is Nash equilibrium, but adapted to a dynamic game that is repeated because the voting procedure is repeated with asymmetric information that is called perfect Bayesian equilibrium. And then we also have the story of the protocol, right? What is the protocol, by the way? So the protocol is a medium used by agents to interact in the blockchain. A prescribed protocol already exists. What is a prescribed protocol is actually the protocol that you download by internet when you want to be a miner of Bitcoin. You download a code, right? This is a protocol. This is the protocol that designer had in mind. But the agents can modify this prescribed protocol to enact their own strategies. And that's the point. They can somehow hack the protocol and to enact their strategies. And so the basic idea is to look at our problem and going from a prescribed protocol, formalize the dynamic game of the voting procedure, see if this dynamic protocol is a Nash equilibrium, learn about other equilibrium that actually can arise even out of consensus, without consensus, and going back to the protocol to see if we can modify the protocol to get a good equilibrium and to achieve consensus. So the voting procedure that we are considering is very, very simplified with respect to the Byzantine fault-tolerant consensus we have seen before. In practice, we have committee members that interact during a sequence of rounds. At the beginning of each round, we have just one committee member that is the proposer that just send a block to the others. When receiving a block, actually, the other committee member decides whether to check or not the validity of the block and whether to send the vote or not. This is what is also called the action space of these agents, considering that checking validity and sending messages are cost. Then when a block receives a quorum of votes that is greater than the number of adversaries, the maximal number of adversaries that we can have in the system, then this block is committed and added to the blockchain. Otherwise, if the quorum is not reached, we move to the next round. If a block is committed, then all the opportunistic players will get a reward. If an invalid block is committed, opportunistic player will incur a big cost which reflect actually the reputation loss of the blockchain which they participate and holding magic currency, because actually they committed something that is not valid at all. So just to give you a very simple idea about that, so it's in this execution example, we have the proposal of the block, all the guys that actually check the validity, threshold is actually there, so for the quorum, so the block is committed. We make some assumptions, so all the message sent or received at the end of the round, so in some sense we are in a synchronous system, and proposer can only propose one block in each round, which implies in practice that we don't have problem of agreement in this particular setting, because it's a very strong one somehow, but still we have consensus properties to achieve that are validity and termination. And we will see that in our setting, these two properties are not always there. Also to say that if actually the quorum for of votes for a block is not there at the end of a round, there is all the players go to the next round. So moving to the next round means to having another proposer. In particular, the end participants are ordered, and participant knows the index, his own index, and then they actually move in round robin fashion. So this is what the prescribed protocol could look like. And in particular, we need to say that if I'm not the designer doing this particular product, I will not read the detail because it's exactly what I said before, it's just pseudocode, consensus is reached. But at the same time, the prescribed protocol implements also a strategy profile. What does it mean? It suggests the same strategy for each player. And we will see if this actually strategy profile is a Nash equilibrium or not. In practice, what the agents can do, other than the action prescribed by the protocol. We say that proposer can actually propose a valid block or an invalid block, and broadcast the block, and as a voter, actually can decide to check the validity or not. If I check the validity, of course, if the block is valid, I can choose to vote or not to vote. If I check the validity, the block is not valid, I can again choose to vote or not to vote. If it is not, the block is not valid, if I choose to not check the validity, I have no validity information about the block, and I cannot still decide to vote, even though I don't know if the block is valid or not to vote. This is what we call the action space. Before entering and before studying if actually the protocol is a Nash equilibrium, we need to also define what are the objectives actually of the different types of actors. And in particular for opportunistic players, their own objective is to maximize the expected gain. We say that actually checking validity as a cost, sending voting messages as a cost, and after each round, if a block is committed, it will the opportunistic player will get a reward. That of course is a reward that will cover the cost, is bigger than the costs. And on the other hand, if an invalid block is committed, then this type of opportunistic player will incur a big cost. For adversary, they have preferences, and this is different than from the opportunistic, of course, and they have lexicographic preferences over the outcomes. In fact, they prefer that the block will be produced and will be committed as a non-valid block. So they prefer that actually to inflict the maximal damage to the system. At the second place, they prefer that the block is never produced, and then as a last choice is to actually get consensus somehow. So they want to destroy validity, then as a second preference, they want to destroy termination. Of course, they can set in strategy in the pseudocode. I said before, these things, this action that we've seen, they can choose to do it concretely by modifying the protocol. And this is just to say that here we can have strategies that actually are enacted through through the pseudocode. Before saying what could be strategies of opportunistic and adversary, we need to fix the power of adversaries, of course. And we do a very strong, weaker. So we have a power adversary that is not so much somehow, in the sense that we have the number of adversary in the community is of course greater than one. So we have at least one adversary. The adversary knows the types of all participants, so they knows who are the opportunistic and who are the adversaries. So in some sense, this is a strong adversary because they can collude with other adversary. But there is an assumption that say that adversary never have the quorum. So if the threshold is null, the number of adversary is less than this threshold. And on the other hand, opportunistic players always have the quorum. And even though it seems counterintuitive, despite this assumption, termination or validity may fail to hold in equilibrium. So studying the best responses of these guys, we can have equilibria in which termination is not there and validity is not there, even though the adversary has not the quorum. And in practice, what is important to say is that to really study what could be the best response of all these guys, you need to also fix what is called the information set of each agent, because as I said before, we have different rounds. So in each round, the participant will learn about other moves, so other participant moves, and then we'll have kind of information about him, but about the others. And in particular, we have two different kinds of information. At the beginning of each round, information set of the participant has a private information and the public information. And the private information is the type the opportunistic player knows. The opportunistic player knows their own type, and the adversary knows all other types. And what is also important to say is that at the beginning of the voting phase, each participant privately knows whether he checked or not the block, but if checked, he privately knows whether the block is valid or not. But this is really private information. And the strategy is just a mapping information set in the action space. So to conclude the talk, I will go straight to the point on the equilibria that actually we found. So first equilibrium is an equilibrium with no termination. There is an equilibrium in which actually no block is ever committed. So it's a kind of paralysis, and this is happen when an agent anticipates that all the others will not vote. That is very easy. In some sense, the intuition of the proof is that voting is a lost cause, because if anticipates that nobody will vote, it's not my vote that will change the output, because the threshold is always at least 2. So if I send my vote, anticipate that nobody will vote, the threshold is not reached. So that's more or less the intuition about it. The equilibrium with no validity is it's a little bit different in the sense that we have that opportunistic propose valid blocks but vote without checking validity. On the other hand, adversary will always propose invalid blocks and will vote for invalid blocks. In fact, in equilibrium, we have the termination is there, but validity is not always there. I say it is not always there is that if the proposer is actually an adversary, we have no validity. If the proposer is an opportunistic one, we'll have validity. But there are some cases in which you will have an invalid block actually committed. And this is actually, I will not go through all these things, but the idea is that somehow there is a phenomenon of free riding here. And somehow voters are there and are so many. So if I'm a voter, I think that the others will do the work for me, will do the job of checking validity for me. Since checking validity has a cost, I will prefer that others will do that at the risk, of course, that the block will be invalid. And this is basically the intuition of the proof. Of course, we have some probability, and the nice thing is that to think that the expected gain and the deviation. So if I take the prescribed protocol and I want to analyze if a validator or a voter will have some interest in following the prescribed protocol, I can see that the expected gain following the prescribed code protocol is in fact less than the expected gain of just having the strategy of not checking at all and vote the block. So the point is that here checking validity and voting for valid block only is somehow interpreted as producing a public good. And here, opportunistic player free ride on the supply of the public good. Sometimes to solve this problem, you can reimburse the cost of making validity checks and should actually somehow solve the problem. The problem here is that this doesn't work for this proposition, for this equilibrium, because validity checks are costly, yes, but are not observable. The fact that they are not observable, you cannot really solve this situation this way. So you need to take this. So we also proved that the prescribed protocol by itself is not an equilibrium. And because we have never say that before, we just say that in the game that actually we modeled, that actually is modeling the voting procedure, you have bad equilibria, but we never said that the protocol itself is not an equilibrium. It could be, but in fact it's not. And the problem is that here, the problem is that, as I said before, the opportunistic players somehow are pivotal in voting when you can have a prescribed protocol that make them pivotal in voting to get the quorum, but not in checking validity. So they really need to check validity to always have be pivotal, sorry, to check validity to really be assured that no valid blocks will be ever committed. So question could be, is there any good equilibrium? And in fact, there is one, and in particular, to get this pivotal behavior of voters to check validity. I will not enter in all the details because I know that we don't have so much time remaining, but the idea is of the equilibrium is that actually the voters, validators are separated in two sets. So you have a subset that is instructed to check the validity and vote in the first F rounds, and the others will do anything. And there is another subset of validators that will actually just vote without checking. So if you have a subset that check and a subset that doesn't check. So this is the idea. And then when actually around F plus one is reached, then you have that all opportunistic players send a message without checking. So nobody is checking anything. And in this particular equilibrium, if those are the strategy, this is an equilibrium, and this is also a good equilibrium. Why? Because actually proposed blocked by adversarial prayer are never committed, because actually those that will vote will not vote to reach the threshold, or even the opportunistic one. And if T equal F plus one is reached, so the round T equal F plus one is reached, it means that all the adversary already passed before. And we know that actually there is no more adversary there. So the proposer is, of course, an opportunistic one. It will propose a valid block. Then even though the validators will not check the validity, it will be fine, and one block valid block will be committed at the end. So to conclude, what we wanted to know is how to get a good equilibrium. Of course, we cannot get rid of others' bad equilibrium, that's for sure. But at least could we have a prescribed protocol to get a good equilibrium? So a modified prescribed protocol could be the following. The prescribed protocol that we have seen at the beginning, all players are instructed to check block validity. A modification could be to actually instruct to check block validity only those processes that have a particular index lower than a given threshold. And to have these two sets of validators, those that check and those that will not check. It is important to say that in the special case in which actually the threshold nu is equal to f+1, in equilibrium, all opportunistic players are pivotal and then check block validity up to the round f. This is important to say because in this case, particular case, player structures don't depend on their index. So their own strategy doesn't depend on the index. So this implies that to reach consensus, we can do it also with the old prescribed protocol, which instructed all the processes to check the validity, right? So in this particular case, but this one was not in equilibrium per se. Still, we have consensus, and we also have a deviation from the prescribed protocol, which is that at the last round, players deviate from the prescribed protocol because they will send the vote without checking. So they are not following the protocol. So still they are deviating. The prescribed protocol is not in equilibrium, still we achieve consensus, which is something that is quite interesting. Okay, so conclusion, of course, we say that, so maybe the big conclusion I can say is that design a good blockchain consensus protocol with incentives is hard. For this new generation in particular, in which we have voting procedures and coordination problems can really arise. There exists some good equilibria, so it could be nice to find them and to design prescribed protocols that actually get this equilibrium.